Alright, we chose to model membrane rupture problems similar to Dr. Putnam's in-class example problem 7a, and we wanted to learn about the behavior of helium under rapid expansion and investigate mechanical stability of components under stress. And using instantaneous membrane rupture and differences in pressure and volume, we could analyze the energy and entropy of the closed system. And ultimately, we want to analyze the decrease in temperature of the expanding gas before the system reaches thermal equilibrium again. Finally, these results can apply to other systems and real-world applications.
Alright, so we catted this up in SolidWorks, made an assembly out of the stainless steel boxes using SolidWorks sheet metal, found some parts from McMaster and downloaded their CAD models to match up for the temperature gauges, the 1/2-inch NTP nipples, the valve, and then we have our through holes here for the temperature probes. They're identical parts, so when they're going to be made, they're going to be made the same exact volume. And then we'll have these exit holes and entrance holes for creating a vacuum and adding the helium inside of it as well. Alright, so to replicate the real life scenario of the membrane problem, what we did is we have two separate chambers that are closed systems. They're separated by a valve in the middle. They're completely sealed off. One will hold a vacuum, the other one will hold helium of the same volume. And the way that we went about this is we have stainless steel that's completely welded and epoxied closed, so we have a complete vacuum, and then just extra tape for some protection. We did this by laser cutting it and then bent some of the pieces and had the rest of it welded into place and epoxy the pieces. We have Teflon tape to seal the threads on it, manually actuated valves, and then we have our pressure gauge to show our vacuum and to show the pressure differential, and we have temperature probes on top as well to see the temperature in each of the chambers. So that'll show us when we flip one of the switches and have the vacuum and the helium interact, you can see the change in pressure in each of the chambers and the change in temperature in each one of the chambers. And we also have the ambient temperature of the surroundings around. So that'll show us heat flow in and out.
Alright guys, for this part of the project, we're going to do the actual experiment. So we're going to start by creating a vacuum in both chambers. Once the vacuum is created, we're going to hook up and put the helium gas into one of these chambers. And we're going to represent the membrane breaking by opening this pressure valve. So we're going to do that now. So with a little bit of help from someone.
Go.
Okay, so we're going to create the vacuum. We're going to carefully do this. Okay, so we're going to create the vacuum. Let's get this shit into. Alright. Hit record on here. Okay, so make sure that's open. Alright, ready? So we're going to initiate the vacuum now. We're going to try to get as much vacuum out of here as possible. So 3, 2, 1. So close this one first, right?
That's good.
A little more. And so we have vacuum in chambers now. So now what we're gonna do is we're gonna fill this one up with helium. You do that. So we're helium now. We're at about 50 kpsi.
Close the valve?
And yeah.
Close that. No, close
Close the other valve.
Close it.
And 3, 2, 1, we're breaking the valve. Alright, so in theory, we should have had a little bit of temperature drop in this chamber. We're going to confirm that.
Alright, so I'm going to talk about the energy balance and entropy balance for our project. So on any energy balance, we're going to have the energy in minus the energy out. And that's going to equal change in energy of our system. So for this is a simple way to write out the energy balance. When we write it all the way out, we're going to have heat in plus the work in plus mass in times enthalpy plus kinetic energy plus the potential energy. And we're going to subtract the heat out, the work out, mass out times enthalpy plus kinetic energy plus potential energy. And this is going to equal change in energy of our system. So specifically for a closed system, we don't have any work in for our system, so we can cancel out that term. For any closed system, we're not going to have mass in or mass out, so we can cancel out all these terms and all of these terms. And work out, we do not have any work out for our system. So all we're left with is Q in minus Q out, and that's going to equal the change in internal energy. So for the internal energy, you can write it out as mass times specific heat at constant volume times T2 minus T1. In our experiment, our starting temperature was T1, ending temperature was T2, and the beginning and end of our system was in thermal equilibrium. Therefore, T1 is going to equal T2, and those temperatures are going to equal the surrounding temperature. Ultimately, this is going to make our change in internal energy 0. So that brings us the heat in equaling heat out. How that works is we have the temperature of our gas over here, and as soon as the gas starts expanding, the temperature is going to drop, and very quickly it'll return to equilibrium at the starting temperature. So heat in and heat out graph. Heat out is the heat coming out with the temperature drop of the expanding gas, and then we're going to have the same amount of heat in to bring our gas back to equilibrium. Alright, so for our entropy balance, we're always going to have entropy in minus entropy out plus the entropy generated, and that's going to equal the change in entropy for our system. So our starting conditions were thermal equilibrium at the beginning and end of our experiment, and then the second volume is going to be twice the first volume. So in a closed system, you're going to have the heat in over the first boundary temperature minus the heat out over the second boundary temperature plus entropy generated, and that's going to equal, in our case, the change in entropy of our gas. Change in entropy of our gas can be written out as the mass times specific heat at constant volume times the natural log of T2 over T1 plus the gas constant times the natural log of V2 over V1. So since T1 equals T2, this term is going to become 1. Natural log of 1 is going to be 0. For this term, V2 is 2 V1, so this is going to be 2 over 1. That's going to become natural log of 2. So ultimately, our change in entropy of our gas will be the mass times the gas constant times the natural log of 2. In turn, this is going to make the entropy generated equal to heat out times the second boundary temperature minus the heat in times the first boundary temperature plus the mass times the gas constant times the natural log of 2. So one very important thing is this term must be greater, this whole entire term must be greater than this term. because for an isolated system, the entropy generated is just mass times the gas constant times the natural log of 2. In this case, if we had an isolated system that was insulated and adiabatic, and a closed system is always going to generate more entropy than an isolated system. So that is why this term must be greater than this term. That way they don't cancel out, since Q out equals Q in. So how that works is the first boundary temperature must be greater than the second boundary temperature. So the first boundary temperature, since our gas is in equilibrium, is just going to be equal to the surrounding temperature. And our second boundary temperature is going to be the surrounding temperature plus the temperature of the gas once it expands. And we're going to divide that by 2 to get a rough average of our boundary temperature. And since this term is less than the surrounding temperature, the overall temperature of our boundary when we have our heat out is going to be less than the boundary temperature that we started with, which is going to make our heat out over boundary temperature 2 greater than this, which makes this statement true.
When you break down the system into its main components, you can see it's mostly just a volume and pressure difference. We ended up using helium in our system. This allows us to mimic an adiabatic system because there's little to no heat transfer. That's because helium has a very high thermal conductivity to it. If you use this in a closed system, you can generate more work out with less heat out, making the system more effective. MRI scanners use this to cool their superconductive magnets when they're doing IMRI scans. Systems like the one we made are already in use today. They're called pneumatic tubes. The banks use them to move the vessels from the car to the inside of the bank and from the inside of the bank back to your car using a pressure differential. Doctors use this to give medications to their patients. This allows one line that is fully reversible depending on the direction that the vacuum is pulled, either allowing to give medication to the patient or take blood from the patient. Chem labs use this to help their samples from getting contaminated, allowing a transfer of gas through a vacuum has less chance of contamination over just transferring it from tube to tube. Helium also can be used to protect electrical components over air because air reacts highly with electrical components. Helium has another advantage in the fact that it's completely inert, making it much less hazardous. Another quality of helium is its low specific gravity. It's about 84% less than air, making any system full of helium weigh much less than air.